The following presentation is for Nexio's BAT-EMC software. In this example, we will be exploring the radiated emissions test according to the MIL-STD-461-G. Let's begin by looking at the EMC software. And here we have a project that's already open. This project was created from a template. And we will first start off with the systems check. In RE102, you're required to do a system check prior to doing the test, and then we can perform the test. Let's first examine the requirements by the standard. In this section, they list the frequencies that are required and the requirement to apply a signal that is 6 dB below the limit. And we can look further about how we accomplish that. In this system check, you can see that we have those exact frequencies listed. But let's look at an individual subrange. We have a start and stop frequency and a step size, which is 1/2 the resolution bandwidth according to Table 2. And that's actually no different than the actual test. The difference is that we named the subrange 10.5 kHz to alert the user as to what signal needed to be injected. Now, if this was a OEM, for example, making the same product and testing only to one category or level, it would be possible to fully automate this so that we drive a signal generator as well as we could drive the oscilloscope for measuring the waveform. However, let's look at the dilemma. If we go to the emissions resources and look at a limit, this is a section for MIL-STD-461-G, and if we look at this limit, you can see this applies to the surface ships. We have two different categories, one for above deck and exposed below deck, and then one for below deck. If we visualize, you can see the numbers there. Same goes for the next one, submarines, external and internal, and so on. This is for the aircraft, fixed wing. We have different distances for the length, nose to tail, etc. And then whether or not it's a helicopter and so on. The point is, there are several variations to the limits. So to fully automate for all limits would be impractical. Going back to the project, however, it is really not a difficulty to perform this test and to reference the limit that's required in order to know the levels that need to be generated. This is how it's typically done. But as I mentioned, we could fully automate it. Next, let's look at an actual test. We will assume the system check was done, that it passed, and we can launch the test. It will stay in simulation mode, verify the resources, and the test will begin. We'll just follow the prompts. And as you can see, we just have one complete curve, no tabular data, no extra post-processing. The main purpose for showing this test was simply to show what the competitor's software normally does. Typically, at most of the OEMs or certification test labs, when the test is done, they simply acquire the data as shown here, the graphic data, no further post-processing such as determining margins relative to the limit line or setting up tables for pass and fail. The previous one was called no finals. This one is called with finals, and I can elaborate further. By clicking on a subrange, we can see the same information, the start and stop frequency, all of the settings that would be normally commanded for the receiver, the Roden-Schwartz ESU from the front panel, These are all settings according to Table 2 of the MIL-STD-461-G. And as you can see, input protection on, preselector on, input coupling, the 6 dB bandwidth, and so on. Video bandwidth 3 times that of the resolution bandwidth. No attenuation. And then the excursion span, this is simply for if we were to do a frequency drift check later on. Now under the procedure, we're doing the same pre-scan as what was done before. However, we have this extra layer of filtering called the advanced suspects. If I were to click on this line of script, these parameters were used to generate that line, and same for this line. This can be considered the first section of extracting peaks to put into the table of results. I'm looking for peaks within 6 dB of the limit line. This first pass filter is to make sure that they're 6 dB above the noise floor, and then we're going to look for the 10 highest peaks. This line shows a limit offset of -30, and the purpose for that is for the case when I didn't find any other peaks that were within 6 dB of the limit line, and I just wanted to have some peaks reported. In this case, I would get the 3 highest peaks. As far as the final procedure is concerned, there is no remeasurement. It is simply taking the peak data, comparing it to the limit line in order to create a margin, and then we calculate that if the margin is greater than 0, that would mean it would be a failing peak. Otherwise, it would be considered a pass. Now, there is no requirement to do this extra filtering or organization of the data. This is simply in order to help the engineering brain organize the data better and focus on important things. Next, we can run the test. I will follow the prompts just as before. And there we have it, completed data. Also keep in mind there is the choice to select any peaks, do any remeasurements, and so on. Furthermore, any of the colors can be customized, the curves for the horizontal and vertical, how we identify any of the peaks, and so on. They can be saved as default values. Now when I click on this icon, you will see I have tabular data up above. And if I look, I have these number of peaks that were considered a pass, this number that were considered a fail, and the complete table. Keep in mind that by doing so, we generate this table with the ability to customize each of the labels for the columns and the column order. This was the original peak data. Both of these tables show the correction factors that were applied in order to receive the correct margin. Okay, now I can close that, and I will show one more version of this test with a slightly higher level of sophistication. Simply in this test, if I were to expand and look at a sub-range, you can see the procedure is slightly different. Why? It's an advanced pre-scan rather than the normal pre-scan. And if I look, I'm still using the peak detector, but I'm commanding polarity change. So this is for the customers that have an antenna mast that they can change the polarity. We won't be changing antenna height or anything like a turntable azimuth, which is done for the commercial standards. But we're going to be sharing a similar GUI. I will demonstrate in the next test. Again, starting the test, staying in simulation mode, but you'll see a difference. Here you can see the two polarities mentioned, and of course there's the fixed height. It automatically changed the polarity. This is the prompt to change the antenna. I didn't receive a prompt for changing polarity, obviously. And there you have it. I can look at the tabular data. It should be identical, which it is. The only difference was the fact that we automatically changed the polarity. Here you can see the all view for all these tabs combined, the individual ones, and so on. We have the ability to command the cursors. Areas can be zoomed in, for example, a shift click. And there's a variety of things that could be done if more measurements were required, such as during a troubleshooting session. I will end this test. And now we can explore generating a report. Let's try this test, for example. I can right-click on it, select Report, and then I will choose this report template. Nexio provides generic templates, and we also assist customers on generating their own. I can call this 102, and I will call it New, just to give it a name. Click Save, and then you can see the dialog box as information is extracted from the test results and put into the new Word document according to the template. In the template there are tags for each one of these elements. When the report is complete, you now have the ability to view the report. Here we have the completed report, and if I were to have filled all the information in the follow-up sections and any other areas, it would have been filled in, but obviously there are some blanks. And as I scroll down, you can see the information. These settings reflect what were used for the different subranges. The equipment used is also listed. The graphs are inserted. If I was to zoom in, you can see that the graphs include a legend so that the individual aspects of the graphs can be understood, such as the limit lines, horizontal and vertical curves, the cursors that are marking the peaks, and so on. All that is configurable. Another thing to mention is that in the follow-up sections, it would be possible to insert photos, have links to where the photos are located on a folder, and so forth. In the instance where the equipment under test is very large and the antenna position needs to be changed, it would be simply a matter of duplicating the previous test. For example, I could duplicate this one and I could change the name to antenna position 2, for example, and then repeat the test. This concludes the Nexio presentation. Please be sure to check out our other presentations on other subject matter, as well as a variety of test cases. Thanks for your attention.